Welcome to The Explainer. I am so pumped to have you here today. We're tackling a massive topic. We are going to completely demystify blockchain technology. We're going to break it down literally piece by piece into its fundamental building blocks. So by the time we wrap up, you won't just know what a blockchain is, you'll have a rock-solid grasp on exactly how and why it actually works, without all the hype. We're taking the complex and making it crystal clear. Let's get into it. Here's our roadmap for today. We'll be hitting 6 main stops, starting with 1, the problem with trust, then 2, anatomy of a block, 3, reaching network consensus, 4, making a transaction, 5, programmable smart contracts, and finally 6, building the Web3 ecosystem. I want to anchor our entire discussion right here on this one, frankly, profound idea: a shift from brand-based to math-based trust. Think about it. For the longest time, if you wanted to send any sort of value online, you absolutely had to have a trusted middleman, like a bank or a payment processor, just to keep the books straight and stop people from double spending. You basically had to trust a brand. But then, this pseudonymous figure, Satoshi Nakamoto, drops a white paper that, well, it changed everything. It gave us a coordination mechanism for people who fundamentally don't trust each other, a way for complete strangers to agree on a single shared truth using pure cryptography and economic incentives. No central boss required. Which brings us to Section 1, the problem with trust. Look, centralized systems have centralized points of failure. When one single company controls the servers, they can freeze your accounts, they can reverse transactions, or they can just quietly change the rules on you without asking. A decentralized network completely removes that single point of failure. There's literally nobody to bribe and nobody to censor your actions. Moving right along to Section 2, anatomy of a block. So look at how these 5 specific properties come together to create this unforgeable digital fingerprint, which we call a cryptographic hash. Think of a hash function like a giant math meat grinder. You feed any amount of data into this algorithm, and it always spits out a fixed-length string of characters. It is completely deterministic, meaning if you put in the exact same input, you are going to get the exact same hash out every single time. It's one way, meaning you literally cannot reverse engineer the original data just by looking at the hash. And this is the cool part. It has an avalanche effect. If you change even one tiny character in your original input, the output flips completely. It looks totally different. Plus, it's collision resistant, meaning it's mathematically infeasible to find 2 different inputs that give you the exact same hash. Now, inside a blockchain, a block is essentially just a bundle of transactions, a block number, the hash of the previous block, and this special thing called a nonce. Nonce literally stands for a number used once. To actually get a block added to the chain, the network poses this massive global trial and error puzzle. The nonce is the one and only field a miner is allowed to freely change so they can try to make the block's final hash meet a ridiculously difficult network target. We call this trial and error sprint proof of work. To give you some perspective on just how insanely hard this puzzle is, the Bitcoin network is currently crunching through hundreds of trillions of these guesses every single second, just to find that one right nonce. You know, this brings up a super fascinating question. Since this whole ledger is public, what happens if some bad actor decides to just go back in time, tweak a transaction in an old block, and pay themselves? How exactly does a blockchain defend itself against someone tampering with history? Well, it triggers what we call the cascade effect. And this is the true magic of immutability. Remember that avalanche property we just talked about? If someone edits a past transaction, that old block's hash completely and instantly changes. But here's the catch. The next block in the chain is still holding on to the old hash. So boom, instantly the link is broken. The entire chain downstream literally shatters. If an attacker wanted to actually hide this sneaky change, they would have to do the near impossible, redo all that massive proof of work for the tampered block, and then remine every single block that came after it, all while racing to catch up with the rest of the network. Because of this, old data becomes, for all practical purposes, permanent. And that leads us to Section 3, reaching network consensus. So we've got thousands of independent peer-to-peer computers, we call them nodes, all holding a copy of this ledger. How on earth do they agree on the actual truth when there's no central referee calling the shots? Well, they need a way to stop someone from just spinning up a million fake identities to outvote everybody else. That's called a Sybil attack. Proof of work solves this by making network influence cost real-world resources, computation, and electricity. You can't fake that. But as you probably know, many major chains have now migrated over to proof of stake. In proof of stake, getting influence means you have to lock up real capital as collateral. If a validator tries to cheat the system, their staked collateral gets slashed. They lose their money. So proof of stake maintains that critical Sybil resistance, but because you aren't doing those massive computational races, it drops the environmental cost by roughly 99%. It's a massive shift. Okay, so the absolutely crucial thing to grasp here is that proof of work or proof of stake is really only half the puzzle. It just decides who gets the right to author the next block. But what happens when there's a disagreement? That's where the longest chain rule comes in. Nodes are programmed to always accept the valid chain that has the most accumulated work as the one true history. And when you put those two together, Sybil resistance plus the longest chain rule, you get Nakamoto consensus. Now, sure, someone could theoretically rewrite recent history if they somehow managed to control 51% of all the network's resources. But on a massive, globally decentralized chain, doing that becomes astronomically expensive. It's not that blockchains run on some magical, unhackable fairy dust. It's just that the math makes attacking them financially ruinous. All right, let's look at how we actually use this in Section 4, making a transaction. Everything starts with a one-way cryptographic journey. First, you have a private key. Think of this as a super secret number you have to keep totally hidden. It is literally the master password to your funds. From that private key, complex algorithms mathematically derive your public key, which is perfectly safe to share, kind of like your email address. And finally, that public key gets hashed down into a shorter address, which is the string of characters you actually give people when you want them to send you funds. Now, here's a mind bender. A crypto wallet doesn't actually hold your coins. Nope, it only holds your private keys. The golden rule in this space is absolute. Not your keys, not your coins. If anybody gets their hands on your key or the seed phrase used to generate it, they completely control your account. No takebacks. So when you actually want to move some funds, your wallet takes your private key and signs a transaction, creating this unforgeable digital signature. Then that transaction gets broadcast out to the network and just hangs out in the mempool. You can think of the mempool as a giant digital waiting room for all the pending requests. Block producers come along and pick transactions out of this waiting room, and yeah, they usually prioritize the ones paying a higher gas fee. Gas is just a measure of the computational effort required, and those fees pay the node operators while also acting as a clever way to ration the limited space inside a block. Once your transaction is actually mined into a block, it's settled, and it gets mathematically harder and harder to reverse with every single new confirmation block that gets stacked on top of it. Now, let's step things up a notch in Section 5, Programmable Smart Contracts. So Bitcoin was brilliantly designed to be this incredibly secure store of value and payment network. It's essentially digital gold, and its scripting language was intentionally kept very limited for security reasons. But Vitalik Buterin, the creator of Ethereum, looked at this and envisioned something way broader. Ethereum took that exact same blockchain foundation, but added a general-purpose programmable layer right on top of it. Instead of just sending digital money back and forth, the network could now run arbitrary code. This basically transformed the blockchain from a simple ledger into a decentralized worldwide computer, a total game changer. And this on-chain code takes the form of a smart contract. The best way to think about a smart contract is like a digital vending machine. You walk up, insert the right amount of funds, punch in your selection, and the snack drops automatically. There's no clerk checking your ID or deciding if they want to give you the snack. Once a smart contract is deployed to the blockchain, it executes its instructions automatically the second its conditions are met. It's immutable, meaning literally no one can alter its terms after the fact, and it's 100% transparent. What this gives us are truly trust-minimized, unbreakable promises, simply because they are enforced by a global network of math, rather than some executive sitting in a boardroom. But we do run into a bit of a roadblock here, known as the Oracle problem. See, because a blockchain has to be completely deterministic so that all those thousands of nodes can perfectly agree, it operates like a sealed-off walled garden. It can't just reach out to the internet to securely fetch real-world data, like livestock prices or the weather, or even generate true randomness. To fix this, we use what's called a decentralized Oracle network. This is basically a group of independent messengers that securely fetch external data, verify it, and bring it on-chain. This effectively bridges the gap, allowing smart contracts to actually interact with the real world without accidentally reintroducing a centralized point of failure. Which brings us to our final stop, Section 6, Building the Web3 Ecosystem. By combining that rock-solid on-chain logic with real-world off-chain data, we create hybrid smart contracts, and these are the engines powering the whole overarching narrative of Web3. Let's do a quick history check. In Web 1, the internet was this open, permissionless frontier, but it was mostly static, read-only content. Then came Web 2, which gave us the amazing dynamic interaction we're used to today, but it became heavily permissioned. All our user data got locked up on centralized company servers. Web 3 is the grand vision of taking all that dynamic interaction from Web 2 and returning it to the permissionless open ethos of Web 1. It's a new era where you actually own your data, and you can hold a real stake in the underlying protocols you use every day. And right now, this ecosystem is just bursting with decentralized applications, or dApps. You've got DeFi, decentralized finance, where complex things like trading and lending are running entirely via code, totally bypassing Wall Street banks. Then you have DAOs, which are basically reinventing human coordination by letting organizations govern themselves transparently using on-chain smart contracts. We are seeing provable, verifiable ownership of unique assets through NFTs. And to handle the absolutely massive global demand for all this, we have rollups. These are layered 2 protocols that batch thousands of transactions off-chain, neatly solving the base layer's scalability limits. Now, as we navigate this wild ecosystem, it is absolutely vital to remember one thing. This ledger is radically transparent. It has to be to prevent backroom deals. However, users maintain a state called pseudonymity. Your accounts are identified by public addresses, those long strings of letters and numbers, not your real name. So while your entire transaction history is completely public for anyone to see, it actually takes quite a bit of effort to link that random public address back to your real-world everyday identity. So it's not true cloak and dagger anonymity. It's more like a highly transparent pseudonymity. So we have covered some serious ground today. We moved from the core problem of trust, explored cryptographic hashes and Nakamoto consensus, and zoomed all the way out to this wildly programmable Web3 ecosystem. And it all brings us to one really profound conclusion. Think about this. If decentralized mathematics can flawlessly execute and verify our agreements completely transparently and permanently, which traditional institutions in your daily life do you still truly need to trust? Thank you so much for joining me for this explainer. I really hope this deep dive completely changed how you see the future of coordination. See you next time.